Hi folks, this is Calc 3 Checkpoint Quiz 9. We're given a function of two variables and we're asked to show it's differentiable at all points in the plane. So how do we go about doing that? Well, we can go back and appeal to the definition of differentiability, which you'd sooner forget, or we can use our power tool, which is our theorem. The theorem says that if fx and fy are continuous for all points x, y, then f is differentiable for all x, y. So we'll just inspect the first derivatives here and check them out. So let's take fx, xy. So we treat y as a constant, take the derivative with respect to x. We're going to get 12x minus 12y. I take the partial derivative now with respect to y. I'm going to get negative 12x plus 3y squared. If I look at both of these guys, these are continuous everywhere. So the theorem tells us then that f is differentiable everywhere. So that'll do it for 1a. Alright, in part B we're asked to find the gradient f of x, y, and here I've recorded it then, our original function. So the gradient of f, remember this is our very first example of a vector field. And how do we get that? Well, in the x component we take the partial derivative with respect to x. In the y component we take the partial derivative with respect to y. And so we did this already in the first part to check for differentiability. So we get 12x minus 12y and negative 12x plus 3y squared. And so that's our gradient, and that's all we need to do for part B. Okay, in part C we're asked to find the derivative of f at the point 1, negative 1 in the direction of this other point. So we're going after a directional derivative. So that's the first thing we get out of this. And there are two ways to go about finding the directional derivative. There's the painful limit definition, or we can use the fact that since f is differentiable, we can take the gradient at the point we care about and then dot it with the unit vector direction. So there are a couple things we need here. We need the gradient at the point 1, negative 1, and then we need the unit vector u hat. Let's go after the unit vector u hat first. So how do we find that? Well, here's a rough schematic of the situation. We want the derivative at 1, negative 1 looking in the direction of 611. So I can find that vector u and then normalize it to get u hat. So how do I get the vector u? It's the old terminal point minus initial point. I finished up at the x-coordinate 6. I started at the x-coordinate 1. I finished at the y-coordinate 11. Started at the y-coordinate negative 1. So when I simplify this, I get the vector 5, 12. In order to normalize it, I need to get its length, its magnitude. So what's the magnitude of u? I take the square root, I square the components, and that's a 5, 12, 13 Pythagorean triple. So I'm going to get the length of u is 13. So this leads me then to what u hat is. U hat is 1 over the magnitude of u, which is 1/13 times 5/12, which is 5/13, comma 12/13. So that gives us the direction. Well, now we need to go back and recall what the gradient was. Okay, so here's what the gradient worked out to be. I need the gradient then at the point we care about, which in this case is 1, negative 1. Substitute x equals 1. I get 12 minus a negative 12. I get a 24 out of that. x equals 1, y equals negative 1, negative 12 plus 3, that's negative 9. So, the directional derivative of f in the direction of u at the point 1 comma negative 1, that's the gradient of f at 1, negative 1, dotted with the unit vector. That's 24, negative 9, dotted with 5/13, 12/13. So on the top I get 24 times 5, which is 120 13ths. Multiply this, so it's going to be subtract 9 times 13. That's minus 108 13ths. And so for my grand total, I get 12/13. And that'll do it for 1C. Alright, number 2, we're given a function of 3 variables. We're asked to find a normal vector to this surface at this point. Okay, so the surface in question here, f of x, y, z equals 0, would be the surface x squared plus y squared minus z equals 0. And as a quick check, if we plug these numbers in, if I look at 3, negative 4, 25, sure enough this is on the surface because 3 squared plus negative 4 squared minus 25, is that equal to 0? Sure enough it is. So that works. Okay, so this describes a surface. We're asked to find a normal vector to the surface at that point. And so we think back to properties of gradient, and what's going to do that? The gradient of f at that point will be the vector we need. Okay, so to that end, let's find the gradient of f of x, y, z. So I take the partial derivative of f with respect to x, then the partial derivative of f with respect to y, and the partial derivative of f with respect to z. So this is just the natural extension of the gradient in 2 dimensions. So I get 2x, 2y, negative 1. And so my final answer here, I'll do it in blue, I'll do it in red to point it out since it's near the bottom. My normal vector then is the gradient at the point 3, negative 4, 25, which in this case is going to be, when x is 3, I get 6. When y is negative 4, I get negative 8. And then I get the z component is always negative 1. So that'll do it for number 2, and that'll do it, in fact, for quiz 9.